Hi, my name is Alexa Vitti, and this is lab number 4 for Physics 2211, Oscillating Spring. So the purpose of this lab is to investigate the motion of a mass oscillating on a spring. So in order to do this, we use Tracker to analyze the position of the mass at different time intervals, and then we also create a GlowScript computational model to predict the object's motion and energy changes. So the goal of the lab is to evaluate whether the system follows the energy principle. And the main result is that the system's total energy remains constant at zero, which shows that it does follow the energy principle. So some fundamental principles important for this lab include Newton's second law, which says that F net equals the derivative of momentum with respect to time, which equals the mass times the acceleration, which also equals the force of the spring plus the gravitational force. And then the energy principle, which says that the energy of the system is equal to the work done by the surroundings plus Q. And in this lab, our system is going to be our spring, our mass, and our Earth. And we've made our surroundings nothing, which says that the work done by the surroundings is zero. And then some useful equations for this lab, which are all derived from these two principles, include the velocity and position update formula, the formula for kinetic energy, formula for gravitational potential energy, and the spring potential energy. So for our initial conditions, which were obtained from our preview video for this week, so the mass of the object was 0.402 kilograms, the stretch length of the spring was 0.7 meters, K value was 6.83 newtons per meter, the L naught was 0.123 meters, and then our initial positions and velocity were obtained from our tracker analysis. So here are those values. So now for our computational model. So for our initial conditions, we plugged in our mass, our initial positions and velocity, and then we also plugged in our constants, so we know our K for our spring and then our L naught. And then we updated these lines for the formulas for the different components of energy. And then for the main part of our code, which was the motion prediction loop, so we iterated through all the time steps and we updated the individual components of energy as well as the total energy of the system. So now to compare our computational model results with our experimental results. So as you can see, for both the X and Y positions, they are pretty similar, but they do start to deviate a little bit, and there are several reasons why this could be the case, which we'll talk about on the next slide. So the first reason could be human error when placing the tracker dots down, so we might not have been at the center of mass every time. Secondly, the video could have been distorted when importing into tracker. And then also, probably most importantly, the friction and drag force were not accounted for in the code, so there isn't actually nothing in the surroundings in reality. So there is work being done on the system by dissipative forces. So is the energy principle followed? So as you can see in the graph, the total energy is conserved. Delta E does remain at zero throughout, even though the components of energy do fluctuate. So yes, the energy principle is followed. And then when we calculate our average period, we can use estimates for our x of t and our y of t to obtain a more accurate value. So what we did was we looked at our y of t graph, and I used 3 cycles. You can use more to get an even more accurate estimate, but I used 3, and I found 2 dots on the y of t graph that were exactly 3 cycles apart, and then I looked at their respective times and then divided them by 3 to get the average period, and then I did the same thing for x of t. So to obtain a more accurate estimate of the t value, we could average the 2 estimates together, and to get even more accurate, like I said, we could use more than 3 cycles to compute the average period for the y of t and the x of t, and then we could get even more accurate. Thank you.